Logan and I have worked together for many years. It's a little bit this is the first example. For here. I'd love to say like this is the first time for me to recite for everyone. I guess there will be more chance in the future. But I'm not further later. Logan take it over.
Sure. Well, thanks, Tianyu. Tianyu and I have worked together for many years, and it's actually very interesting that this is the first time he's ever presided in a session that I've giving a talk in. So I'm going to talk about our work on deep physical neural networks, which is about training controllable physical systems to do things much like you would train deep neural networks to do things. So first, I want to kind of give like the compressed version of the talk. So in traditional computer science, the way this goes is if you want to do something, you have some function you want to realize, you need to hire a human engineer, or you need to get off your butt and actually make an algorithm. And this is a list of instructions that are then going to be compiled onto a physical system. And physical system sounds really general, right? It's not. It's always digital electronics. It's always integrated digital electronics. Machine learning is a kind of new way of switching this up. Instead of having a human engineer, we have a procedure for machine learning, so learning the parameters of a so-called parametrized algorithm, like a deep neural network. But at the end of the day, you still have to compile it onto a physical system, and it's always digital electronics. So what this talk is about is something we call physical neural networks, where we're trying to go directly from the desired function straight to the physical system. And what we're doing is we're copying this idea of learning parameters of an algorithm. Rather than mathematical parameters, we're learning physical parameters of controllable physical systems arranged in a network. Oh, I should just mention the people that I worked with on this. In particular, Tatsuhiro Nadera was my partner through all of this. And Peter McMahon, he's the PI of the group where all this took place. So with that said, I had the great privilege to help start Peter's group at Cornell starting in 2019. But I've since moved very recently to Yale to start my own group. You can see there's a sort of familial resemblance there. And people often ask, like, what do I work on? And I'm so early in my career, I don't always have a good answer. But what I end up telling students is kind of thing like this. And if that gets you excited, you should know that I am indeed hiring. Okay, so with that, motivation for this, the inspiration for this are mathematical artificial neural networks. So what deep learning is to a physicist, it's just high-dimensional curve fitting, right? You have some function that has some mathematical parameters. You want to perform some function. You want to implement some function that operates on a high-dimensional vector, like this image, and you want to transform in these high-dimensional inputs to some desired output. For example, you might want to determine whether an image shows my dog or Hero's cat. But deep learning is more than just high-dimensional curve fitting. Deep in deep learning, it doesn't mean deep thought and really profound ideas. What it means is multi-layer neural networks. It means there's a sequence of functions that each have their own parameters, and we feed the output of each layer into subsequent layers. And this hierarchical or compositional ansatz turns out to be incredibly effective. It's really, really effective at describing a lot of natural problems, because it allows the deep neural network to break down the task into a set of easier subtasks. So when you start with a deep neural network, you just have a bunch of random parameters, and it doesn't do anything useful at that point. So the learning in deep learning is that you have to actually teach it what to do. So you have you have labeled examples. You use those labeled examples to iteratively update the parameters until it does sufficiently well. And then once you've done that, you can now deploy it on new unseen data, new cats and dogs, with fixed parameters. And this is called inference. So deep learning, I'm sure you've heard of it. It's kind of blowing up. There's many more applications of it every year. And people are making bigger and bigger models, more and more parameters, more and more compute, much faster growth of use of compute in both inference and training than Moore's law. And this is sort of scary because it's like, well, you know, these people are starting to use more and more compute. It's starting to get more and more expensive, sort of a little bit frightening. It's also very motivating because it's actually kind of remarkable that it's so easy to make these things do better. I say so easy, that should be in quotation marks. But it's also an opportunity for people like those of us in this room. And what I mean by that is that neural networks, of course, are ideal for analog hardware. This has been known from the very beginning. This is Frank Rosenblatt at Cornell, and he is the inventor of the perceptron. And here is his analog optoelectronic implementation of that at Cornell very early on. Today, people are carrying on in this tradition with this new motivation, developing analog physical systems to do neural network calculations more efficiently. Analog electronics, superconducting electronics, as we recently heard about, and in optics. And optics is the area that I'm most familiar with. That's where myself and my colleagues tend to mostly concentrate our efforts. So the way that all these things work is math, physics, isomorphism. So here's a neural network layer, a typical neural network layer, and the most expensive part is connecting these neurons together, and that's done by a matrix vector multiplication. So as one prominent example, this is a crossbar array, an analog electronic crossbar array. And if you go through and you treat each one of these junctions as a resistor, you can show that just applying Kirchhoff's laws, this system ideally implements a matrix vector multiplication. But I say ideally, because achieving this rigorous isomorphism, making physics do what we want it to do, making it exactly implement that math, is notoriously difficult. There are hundreds, if not thousands, of papers, engineering journals on trying to get that to happen. And you have to sacrifice a lot of different things, in particular the hardware cost and the efficiency of implementing calculation in order to make that happen. So a motivating question for our work was, you know, how much of this isomorphism do we really need? Can we kind of loosen things up? And that brings me to physical neural networks. So neural networks built out of these layers. Each one of these layers is just a controlled mathematical transformation. It's just converting one vector to a new vector, and there's some parameters to control that nonlinear transformation. Well, the key insight in our work is that programmable physical systems give us a controllable physical transformation, which can represent a mathematical transformation. It's also just a physical transformation in of itself. To really spell this out, we can have a physical system. We can prepare it in some initial condition. We can then let it evolve for some period of time. And we can then measure it later on. That will perform a transformation of that initial state. And we can control that transformation by adjusting parameters, right? Like where I put the pivot point of this pendulum. This, of course, is a very general thing. Just to give you another example, consider a system of coupled pendula. It doesn't have to be linear or nonlinear. We're assuming it's nonlinear. We can encode data by the initial angle of each pendulum. We can control the coupling. We can control the evolution of this system, the transformation it does to that initial condition, controlling the coupling between these oscillators. And like I said before, we can just read out the result by measuring the oscillator angle later on. So with this kind of foundational insight in place, just, it's so obvious, it's kind of hard to call it an insight. But nonetheless, with that idea in place, we can now construct physical neural networks. And what physical neural networks are, they are networks of controllable physical transformations. They're trained to perform physical functions in a similar way to how artificial neural networks are trained to perform mathematical functions. But let's not get too carried away with the word similar. The most important thing, perhaps, is that this is a flexible analogy. This is a loose analogy. We can use whatever physics we want. Most importantly, we can use the physics that physical systems want to do. We can build computations out of the transformations physical systems wish to do without forcing them to be something that they're not. So maybe everybody already finds this to be an obvious thing that's going to work. I want to give you some reasons why we thought this was going to work out. First one, there's kind of a proof of concept has been pointed out of using high-dimensional noisy nonlinear analog systems to do very efficient machine learning. This thing does not at all resemble a deep neural network, or it only very loosely resembles a deep artificial neural network. In fact, all physical systems kind of have many similarities to deep neural network architectures. Another thing that kind of motivates us that maybe this will work is an area called neural ordinary differential equations. This is a field that is focused on looking at essentially continuous time neural networks. They view deep neural networks as a kind of continuous time controlled dynamical system. And this is motivated for using less memory in the training process because they can use optimal control theory to do that. But nonetheless, it certainly insinuates that you could use physical dynamical systems to do machine learning. But the most important inspiration, the most important thing that makes us think that this is going to work out is a field called physical reservoir computing. So physical reservoir computing is born from the idea of random feature learning. So this goes by many, many names in the literature. Some of them are better than others. But essentially what it is you have data, you have some data vector, you send it into a transformation, but this is a fixed high-dimensional nonlinear transformation. And outputs of this transformation, we call them features. They're orthogonal nonlinear functions of that input data. And we can then train a linear layer, which just assembles linear combinations of those features. And we can then use this as our model to approximate functions of X. In physical reservoir computing, just replaces that feature generator with a physical system. So we encode data into the physical system. Later on, we measure things about it. And those measurements that we perform are these features that we can then linearly combine. And a truly marvelous diversity of systems have been used to do reservoir computing, as we've already seen at this conference. A bucket of water, an octopus's arm, or a silicon version of that. Many of these actually do quite well, as we saw in the morning session. And actually, so I want to pause here. The reason I really thought that this field was really fun to be in, the reason that I was drawn into this is not where I did my PhD, is that it unites all these different physical systems together. I was always somebody who really had a hard time deciding what physical system I was interested in. The physical reservoir computing was just so cool to me that it united all these different kinds of diverse people and perspectives to one common field. And that's why I really would like to thank the organizers for being so bold and bringing together such a diverse set of people and fields. This is what is required to make this field be what it needs to be. So it's not just a cute thing that you can do to make yourself feel good. Many of the features that can be computed physically can be computed with vastly more energy efficiency that can be done with digital electronics. And here's an example from Sylvain Jagon's group in Paris, where they're just finding a laser beam through a complex medium, kind of like white paint. And this system, it's not even that optimized. It's like literally kind of off-the-shelf components can already perform random matrix multiplications 1,000,000 times more efficiently than a GPU. And if you're interested in that, there's a poster by Fei that is going even beyond reservoir computing. So this is all the context for when I started my postdoc. I started working with Peter around 2018. So myself and Hiro and Peter kind of grappling with this thing. There's these two things that we love, and often when you have two things you love, you feel like you should bring them together. Not always a good idea, but sometimes a good idea. And what we came up with was PNNs. And I should just say, like this wasn't in a vacuum. There was many people thinking thoughts along these lines. Some of the people are and words are listed here, but nonetheless, this is our approach. So I always like, when people know what reservoir computing is, to explain physical neural networks as kind of an evolution of reservoir computing. It takes the best of deep learning, we think are the most important ingredients, but it combines it with the physics first opportunism physical reservoir computing. If we can get this to work well, we can automate the process of doing physics first computation. And naturally, because we're using physical systems in the way that they want to be used, letting them be what they want to be and doing computations, energy efficiency gains and speed ups in performing these types of calculations. And this is not what we originally were motivated by, but because we're now doing computation in the analog physical domain and these weird domains that are not digital electronics, we can start thinking about computation in a way that is not living in this digital world separate from you and I. We can think about computation as immersed in a physical analog world, make things like sensors or even micro machines, or give us a new perspective on self-organization or functionality in biology. So I want to give you now an example of a physical neural network. We're going to go back to this system of coupled pendula. And what we're going to do is the age-old problem of classifying images. We're going to classify images of clothing items here. We're going to encode the data, control the transformation of the system in just the way that I described before. And by the way, if you're interested in this example, all the code is available here on GitHub, so you can start playing around with it yourself. So physical neural network is a network of controllable physical systems. So this is what that network looks like. Hero came up with this design. It's based on something called an MLP mixer. If you know what that is, great. If you don't, it doesn't matter. The most important thing is that there's multiple layers. So there's multiple physical systems, and the output of one physical system is serving as the input to a subsequent one. So there's a potential for a hierarchical computation to take place here. And to give you an example of what the dynamics of the system look like once we've trained it, this is the sort of hidden oscillators inside this big network. You can see this sort of non-trivial dynamics in phase space. And there's 10 oscillators that we use to encode the prediction of the network. These are the ones that we look at to say, what does it think article of clothing is? In this case, we put in an image that is corresponding to a t-shirt. And at the time in which we measure the oscillators, you can see that the amplitude, the angle of that oscillator is the highest of any of the oscillators. So we can train this network, and eventually we can get to about 90% efficiency, or sorry, 90% accuracy, which is not like the best thing that has ever been done in the world, but it's actually pretty good. It's really quite good for this task. This is not MNIST hand-printed digits. This is a significantly more difficult task. So this is actually really quite decent. So we were doing this work. There was kind of a really nice moment that lives in my memory where Hiro and I were sitting in the basement of Clark Hall, which is the applied physics building at Cornell. And we were kind of working through the implications of what we were doing. And we both sort of simultaneously said to one another, can everything be a neural network? Like we had generalized things so much that we worried that maybe we had generalized it to the point where it was meaningless. But actually, the answer to this is not that we were going crazy, but well, maybe it was, but the answer turns out to maybe be something like yes. And Hiro would make me make sure to tell you that it's because you can make a neural network out of something doesn't mean it's a good neural network. But we did make physical neural networks out of many different kinds of things, experimental systems based on mechanics, electronics, and optics. And we can get these things do legit image classification, machine learning calculations with different physical neural network architectures. I'm not going to try and explain each one of these physical systems because this is a broad audience, but if you're interested, you can check out the paper. So, okay. I've been talking about this phase. This is kind of the fun phase where you don't have to think about how you got there. The learning and deep learning, remember, was this phase. So how do we do that? How do we do that for physical neural networks? And the way we do that is a really simple trick. It's kind of a brain dead idea, but it turns out to work really well. And what that idea is, call it physics aware training. And what it allows us to do is to use the algorithm called backpropagation, which is how all deep neural networks in deep learning are trained, and directly apply it with literally basically no changes. We can apply all the same infrastructure, all the same software to control and optimize physical parameters of physical neural networks, as opposed to the mathematical parameters of deep neural network algorithms. And the way it works is we just do everything the same as you've seen so far. We do inference with the physical system. The physical system is doing all the computation. However, when it comes time to estimate gradients, in order to update the parameters so that the physical system better approximates what we would like it to do, we use a digital model. And this could be a physics-based model. It could be a data-driven model. It doesn't really matter. But this thing lives on a computer. And as a result, we can just put all the autodiff infrastructure, all the infrastructure of machine learning we can deploy to making this work well. So some good things and bad things about this. The best thing about it, in my opinion, is we get to use all of the infrastructure of machine learning, and we can apply this to literally any controllable physical system that you would like to use. The bad thing is that in the learning phase, not in the inference phase, but in the learning phase, we need to use a digital computer, which is kind of disappointing if you're trying to avoid using a digital computer. So I'm sort of would like to highlight that PAT, physics-aware training, is not the only way to train these things. In fact, there is now a quite growing competition for what should be the way to train PNNs in a way that does not require us to use a digital computer, in a way that utilizes a physical system to do that learning for us. So that's PNNs. That's the idea of PNNs. That's the proof of concept of PNNs. Now, what can we actually do with this kind of thing? So we set out with this kind of thing in mind, right? We wanted to replace a GPU with a PNN. And an example of this, this is work that was led by Maxwell Anderson, who's a PhD student at Cornell. He analyzed the implementation of large language models in optical neural networks. And he was able to show that because of the fundamentally different physical mechanism by which these calculations are performed, there's a scaling advantage. That is, as you increase the size of the model, optics gets better and better relative to digital electronics in terms of energy efficiency, potentially up to 100,000 times more energy efficient than digital electronics, state-of-the-art digital electronics. You can also because this is in the physical domain, you can put in a physical input to the PNN. An example of that is neural network smart sensors. So in the optical domain, we can do machine vision by, instead of just capturing images with a camera and then post-processing them with a neural network, we can actually pre-process images with an optical neural network. And we can, for example, compress or extract information so that we can get by with a much, much smaller sensor. We can go faster. We can use fewer photons. We can also use this to generate physical systems. The output of this can be a physical system or a physical state. So that could be used, for example, for directing self-assembly or driving a synthetic development process, or for controlling self-organization more generically, just mode locking, which is something that sort of have a fascination with. You can also completely cut out the digital thing and just think about this as a machine, a complex machine that we can learn in the same way we can learn a neural network algorithm. And you can then think about chemical or microfluidic processors that act on these types of physical data, or functional materials, as we've seen, or micro robots that carry out different tasks in the nano world, or analog controllers, as has come up at least once before in this conference. Another example that you've seen is this work from Hiro and Marden on using complex wave propagation. These you can now learn photonic devices, photonics in, photonics out, in a PNN style approach. Oh, I know I'm kind of running out of time, so just want to say a couple things. So the first thing is that we set out to try and make software, hardware, physics informed, but actually software has always been physics informed. Sarah Hooker has this wonderful, eloquent essay describing this, and she calls it the hardware lottery. And Rodney Brooks, a famous roboticist, pointed this out earlier in the context of artificial intelligence. Basically, the constraints of the existing hardware are kind of an invisible guiding hand in determining which algorithms do well, and thus get popular in the research community. But this has been an invisible hand. It has not necessarily been as much on purpose as we would like. So, colleague Jeremy has a nice way of summarizing this, which motivated us to write a perspective article. He describes the algorithms that come from this communal process of optimizing algorithms, say in the machine learning community, as an optimization problem over algorithm space for some metric, like the best artificial intelligence. But the most important thing is this is subject to this constraint. And it's an invisible constraint for a lot of people, but nonetheless, it is a very, very important constraint. So what I encourage you to read this article is, of course, we want to get to the point where it's not a GPU, it's physics alone that is the constraint on the computer's software and hardware that we're making. And if you need more motivation, it also features laser-based aliens, which is the first time I've been able to put those into a paper. So this is the talk. This was the main idea of the talk. And with that, I'd be delighted to take any questions or criticisms you may want to throw at me.
Yeah, I think we maybe have a time for one question or two.
Okay, so I was a little nervous when I saw you were talking after me because I knew I was going to talk about devices. And I knew that you were about to tell us that devices are not necessary. And indeed, my fears are realized. So the one thing devices do for me is you can shine radiation on them, you can vibrate them, you can heat them and cool them, you can characterize them, and then you can block them together and understand rigorously how that system scales. You know, if we cover the planet with this technology, are we at risk at the first, giant solar storm that, everything goes out at once unpredictably? And, are the reliability and robustness and hopes for the rigor in that side?
Okay. That's a good question. I have a sort of cheeky answer to that, and then I have a real answer. Get the cheeky answer out of the way first. So the first thing is that, yeah, these things operate robustly. There's one right here, there's one right here, there's one right here. And as far as I know, when there's a solar storm, they're going to do much better than this. And there's some credence to that in that as we're training these systems, we can really train them to be robust to perturbations. But of course, we can't train them to be robust to catastrophe. So the less cheeky answer is that I am, let's say, agnostic about where we will see applications of these. I actually think that in the near future, maybe even the next couple decades, applications of this approach are not going to be in replacing GPUs and things that are going to go in your cell phone. It's going to be in engineering and controlling complex functionality in systems that we maybe didn't even think about as doing computation before. So I think it's a framework to expand the domain of computer science, not necessarily to replace the paradigms that already exist.
So, great talk.
I guess one question I have, and this is maybe a little bit of an unfair question, but I'm going to poke you a little bit, is everybody's very mean to digital electronics. And the digital electronics is awesome, by the way. It's really, really cool. But one thing you could point out is that to compute anything, you fundamentally need area, energy, and time, right? Those are kind of the three ingredients. And historically, microelectronics has favored, we don't care so much about energy. We can get area by scaling, and time is a big factor. We want fast computation. When you talk about these things, even though you have power efficiency speedups, they're slow. They're way slower in a lot of cases than what you could do when you go end to end with the whole system. Right? Like light goes through the system very quickly, but updating, say, the SLM or like building these other little parts to tweak these tunable parameters is usually quite slow compared to what you could do computationally. And I wonder, like, do you think you face a similar, like that you're just not looking at that other axis, or do you genuinely think that there's like a whole new thing that just I'll never be able to do in silicon that you'll just win entirely on?
So I agree. Silicon electronics, easy to bash, but it is one of humanity's greatest achievements. And as I said to Carl, I don't think that PNNs are going to replace silicon electronics in most applications. Like, you're never going to have this thing be based on a PNN, in my opinion. I want to push back that I think you're wrong, that there are many settings in which a physical neural network in inference be dramatically faster and can be done in a digital electronics.
But I guess what I'm curious about, right, is I think it's often the case because the electronics weren't engineered for that purpose, right? Like if you were to say I have the same time constraints between the two, you could relax a lot of the power restraints on the digital electronics and probably get it to be more power efficient, right? So you're comparing something that was really optimized for one task, like doing things very, very quickly, against something that does not feature that's, you know, and saying that's representative of that entire compute platform. And I think my pushback would be to say, well, no, I could re-engineer that digital system. I could take all I know about CMOS and who knows where I would wind up. Maybe I really can boost the power getting closer to kind of a performance game. And so I think there's some ambiguity in that comparison. I guess that's kind of what I wonder.
All right, that's a good point. I guess just to be, can I be quick? It's sort of well understood that analog computing can be significantly more efficient than digital computing if you can tolerate noise and imperfections. Like this goes back to Carver-Mead. So in some sense, there's no matter, like even if we're building PNNs in the digital electronics framework, or we're building it from the same infrastructure, we should still be able to get that kind of advantage. But yeah, I want to be like very clear, and Carl's question also alluded to this. This is never going to replace digital electronics. I believe that in my lifetime, we will always have digital electronics. This can expand the domain of computer science into new types of physical settings and applications.
That's